In this session, we will continue our discussion on the topic of radioactivity. In this session, we will be looking at artificial transmutation, artificial and induced radioactivity, radioisotopes and their applications, and biological effects of radiation, and some safety precautions that we need to take when exposed to radiation. Now, to start with, we're going to talk about artificial transmutation. We learned earlier when we were discussing about radioactivity, we said that the nucleus emits radiation spontaneously, and that process is known as radioactivity. Now and we also mentioned that radioactivity is not dependent on external forces such as pressure or any external forces. Pressure, temperature doesn't affect radioactivity. There is another phenomena in which a nucleus can undergo change based on an external force. For example, when alpha particles are made to hit nitrogen nucleus, then the nitrogen nucleus absorbs the impinging alpha particle, undergoes change, and it turns out to be oxygen. So effectively what happens in artificial transmutation is the nucleus of one element gets transformed to a nucleus of another element. So if I were to write this as a formula, then I have 4He2. This is an alpha particle hitting a nitrogen nucleus would result in oxygen 17 and then 8 and then 1 proton. So this is the equation I would get. An alpha particle bombarding a nucleus of nitrogen would result in the nucleus of nitrogen undergoing change and becoming nucleus of oxygen with the emission of 1 proton. This is an example of artificial transmutation. So the process in which an external particle interacts with the nucleus of an atom and makes that atom undergo change and results in a newer element, nucleus of a newer element along with the emission of a proton or some other particle is known as artificial transmutation. So in artificial transmutation, the element that gets bombarded by the external particle undergoes change and then becomes a newer element. So this is about artificial transmutation, and this is a typical example of artificial transmutation. I have alpha particle hitting a nitrogen nucleus, and with the resultant that I get an oxygen nucleus and 1 proton. If I were to write this, generalize this and write this, then I can say an alpha particle impinging a nucleus of type X would result in a nucleus of type Y plus B, where B is another particle. So if I were to write it in terms of a diagram, I can say that this is the alpha particle that is hitting the nucleus here. So this is the alpha particle, this is the nucleus. This results in this nucleus getting excited or absorbing the alpha particle that is impinging on that, and then giving out a nucleus of type Y and then giving out a particle B. So this is how I can represent artificial transmutation. So in general, an incident particle such as alpha particle strikes the nucleus, and the result is that we get a nucleus of a different type with the emission of a new particle, emergent particle B. So this process is known as artificial transmutation. So this is about artificial transmutation. Now let us move on to the next topic, that is artificial and induced radioactivity. So when we discussed about radioactivity, we mentioned that radioactivity is an instantaneous process, unaffected by external sources. So whereas when we talk about induced or artificial and induced radioactivity, as the very name implies, ACTIVITY, okay. As the very name implies, this radioactivity is not naturally occurring, but it is artificially induced. So let us look at the process of artificial radioactivity first, then we'll define what is known as induced radioactivity. So we mentioned that when we talked about radioactivity, we said it's an instantaneous process. There are no external forces acting on that. A nucleus emits radiation and undergoes change. Whereas when we talk about artificial radioactivity, we are talking about elements that are otherwise stable, or nuclei of elements that are otherwise stable but become unstable when I make another external particle impinge on this nuclei. So this nuclei becomes unstable at that time and then disintegrates into two different elements. So it becomes, effectively what happens is phenomena of radioactivity is induced in this element or in this nucleus by making an external particle interact with the nucleus. So that process is known as artificial radioactivity. So if I were to write it down, then I can say the phenomena of disintegration, of an otherwise stable nuclei by bombardment of by bombarding them with suitable particles is known as artificial radioactivity. Effectively, it means that the nucleus was otherwise stable. We made a suitable particle interact with that, or we bombarded this nuclei with suitable particle, thereby made this nucleus unstable, and then it disintegrated into two daughter elements. So that process is known as artificial radioactivity. So this radioactivity is artificially induced in this nucleus, otherwise stable nucleus. So let me repeat that the phenomena of disintegration of an otherwise stable nuclei by bombarding him with suitable particles is known as artificial radioactivity. So we have several examples for artificial radioactivity which we will discuss later. But there is another term that is involved here, that is induced radioactivity. Normally what happens is, when we talk about artificial radioactivity, I am making some external particles bombard the nuclei, stable nuclei. So this nuclei absorbs the bombarding particle and then undergoes or emits or disintegrates, emits radiation and then disintegrates into two particles or elements of comparable mass. So that is the artificial radioactivity. Normally what happens is, if the suitable particle stops bombarding the element, then this disintegration stops at that instance of time. So only so long as the particle is bombarding the element or the nuclei, this radioactivity is seen. Once this particle is made to stop bombarding this nuclei, this radioactivity process starts. However, in some cases, even after this particle stops bombarding the nuclei, this element continues to disintegrate, and that process is known as induced radioactivity. Effectively what we have done is, by making some suitable particle bombard the nuclei, we are inducing radioactivity into that nuclei. So if that radioactivity continues even after I remove the bombarding particle. So that process is known as induced radioactivity. So let me define induced radioactivity as induced radioactivity is if the bombarded element continues, keeps on degrading, keeps on disintegrating, even after the bombardment is stopped, the phenomena is called induced radioactivity. So this is the definition for induced radioactivity, and this is the definition for artificial radioactivity. So if the nuclei is not artificially radioactive, it cannot have induced radioactivity, which is very obvious here. So for example, I hope this definitions are clear. Let me give a couple of examples for induced artificial radioactivity. So it has been known that boron B10 5, when bombarded with helium or alpha particle, undergoes change, and then I have 14 N7, which effectively becomes 13 N star. This is an excited state plus 1 neutron. And now so this nitrogen continues to disintegrate, giving one positron. So this is clearly a case of induced radioactivity. Half-life of 13N7 is 11 minutes. So we also have additional data here. It says that half-life of 13N7 is 11 minutes. So half-life of N137 is 11 minutes. Note that when we talk about artificial or induced radioactivity, the same laws that we talked about, radioactivity decay and half-life, mean life, etc., still hold good in case of artificial and induced radioactivity. So the processes we saw here about decay constant, half-life, mean life are still valid for artificial and induced radioactivity. There are a couple more examples given in the book. For example, says that almost all the elements can be made artificially radioactive. Almost all the elements can be made artificially radioactive by bombarding them with various particles. As example, we have sodium with sodium giving out magnesium, and then aluminum and alpha particle giving out phosphorus. So these are some of the examples we have here. So with this we have covered artificial and induced radioactivity. Now let us look at how do we prepare artificially radioactive materials. So how do we prepare artificially radioactive materials? We just saw what is artificial radioactivity. Now let us see how to prepare artificially radioactive material or nuclei. So there are a couple of ways in which we can do that. One is to place the atoms or element in a nuclear reactor. We mentioned that when we talked about nuclear reactors, we said that because of the nuclear fission process, energy plus particles, suitable particles are released as part of fission process. So those released particles can be made to impinge on the atoms of this nuclei, and then thereby we can induce artificial radioactivity. As an example, we have P15 plus 1 neutron giving 32P15 plus gamma ray. The other way of making artificially radioactive material is to bombard these elements, as we mentioned, to bombard these elements with external particles such as deuteron from particle accelerators like cyclotron. So we can use cyclotron So another way of doing it is using particle accelerators. Such as cyclotron. So we can use particle accelerators such as cyclotron to generate high energy particles, and those particles can be made to impinge on this nucleus of these atoms and make them artificially radioactive. So these are two ways of making or preparing artificially radioactive material. One is to place the atoms in nuclear reactors, and the other one is to make use equipment such as cyclotron and generate the particles that impinge on these atoms, and thereby make these atoms as radioactive, artificially radioactive. So these are example for this is sodium being bombarded with deuteron, or rather magnesium being bombarded with deuteron to produce radiosodium. So radiosodium is made using this method of using cyclotron. So this covers artificially induced radioactivity. Now let us look at the next topic, that is radioisotopes. So we are now going to talk about the topic of radioisotopes. Let us now look at the topic of radioisotopes. We know that the nucleus consists of neutrons and then so these are protons, these are other ones are neutrons. So we know that neutron consists of nucleons, or rather nucleus consists of protons, positively charged protons, and neutral neutrons. We also mentioned that when we say A, this stands for the mass number. Mass number is a number of particles inside the number of elements or number of particles inside the nucleus, which includes number of protons and number of neutrons. We also said that Z or Z stands for the atomic number, which is the same as number of protons. So number of protons is represented as Z, and then this is number of nucleons. Nucleon is a common term used for proton as well as for neutron. So A is the mass number and Z is the atomic number. Now it is this number of protons and effectively the number of electrons that decide the chemical property of a material. Now if I have two materials or two elements which have same atomic number but different mass number, such elements are called as isotopes. So isotopes effectively have isotopes or elements, or I can even say nuclei, that have same mass number or rather that have same atomic number but different mass number. That means the number of neutrons in these isotopes are different. So I have an element and its isotope. The number of protons or the atomic number in these two nuclei are the same, and therefore they are chemically identical. But the different mass numbers, they have different mass numbers. That means they have a different number of neutrons in them. So these are such elements are called as isotopes. And now isotopes that are radioactive are called as radioisotopes. Radioisotope. So radioisotopes are isotopes that are radioactive, and generally this radioactivity is because of artificial or induced radioactivity. So it has been found that we can get radioisotopes for almost all the elements. For almost all the elements we can generate or we can create radioisotopes. So there are various applications for this radioisotopes which will be going through shortly. So the note says here that there are about 800 known radioisotopes at this time, and radioisotopes, as we mentioned earlier, are formed by bombarding the nuclei, stable nuclei, with external particles such as alpha particles or deuterons or neutrons, etc. So with this brief introduction to radioisotopes, let us now look at some of the applications of radioisotopes. So we are looking at applications of radioisotopes now. So let me list down some of the applications here, and we can go over them pretty quickly. We'll now look at some of the applications of radioisotopes. I have listed down some of the applications of radioisotopes over here. So they are broadly classified into industrial applications, agricultural applications, medical applications, biological applications and geological applications. So under industrial applications, as you can see, these are the points we have here. First, it is used in self-luminous paints. Then it's used in wear and tear and lubrication. Then study of alloys and quality control of castings using radioactive cobalt-60, etc. Now when it comes to agricultural applications, they are used to create new hybrid plants using radioisotopes. And then it's used for insect control to reduce the pests, the population of insects. Then it's also used for preserving grains so that grains can be used over a period of time without decaying. It's also used to study the fertilizers and photosynthesis, in the process of photosynthesis. And next, when it comes to medical applications, radiophosphorus and radio gold are used to control and cure blood cancer, also known as leukemia. So radiophosphorus and radio gold are used to control and cure blood cancer. Radioiodine is used to cure what is known as hyperthyroidism. So it's basically for iodine, excess of iodine in the body. So this is hyperthyroidism. To cure that, we use radioiodine. And then radiophosphorus is used to treat skin diseases. So this is about the medical applications of radioisotopes. Now let us look at some of the biological applications of radioisotopes. And radioactive iron is used to study the behavior of red blood cells. And then radioisotopes are used to study the mechanism of energy release by carbohydrates. And finally, when we look at geological application, some of them are very evident and probably you would have already heard of that in some other context. First is radioisotopes, because we know what is the half-life of a radioactive material. By knowing how many of these particles are still remaining or how many of these elements are still remaining, we can find out the age of rock, age of earth, etc. by use of radioisotopes. Then radioisotopes are used in carbon dating to determine age of samples, that is geological and archaeological samples. So we can find out the age of rock and age of earth. So these are based basically on the half-life and mean life of radioactive materials. So these are some of the applications of radioisotopes. So they are broadly classified, as I mentioned earlier, into 5 categories: industrial application, agricultural application, medical application, biological application and geological application. Now once we have gone through these applications, we are now going to look at biological effects of radiation, and then we'll talk about safety precautions. So the next topic will be to discuss about the biological effects of radiation, how the radiation affect us basically. So we'll now look at the biological effects of radiation. Depending on the type of radiation, the effects of radiation could be different. For example, when we consider alpha particle, they are less penetrating in nature. They can be stopped quite easily because they are basically nucleus of helium, and therefore their size is much higher compared to beta particles, which are basically electrons, fast moving electrons. So depending on the nature of particle or the radiation that is falling on us, the effects might be slightly different. So alpha particles basically cause the skin to get damaged pretty easily. So one of the things that happens is ionization of the atoms in the human body, which cause sometimes some kind of a burning effect which will not heal because the cell itself undergoes change. And that's one of the effects of alpha particle. Beta particles are have got much more penetrating power compared to alpha particle, and therefore the damage is much more extensive. Neutrons on the other hand are not affected by electrical, and basically they are neutral, and therefore they are not affected by electrical or magnetic fields, and since they are neutral in nature, they have much more penetrating power. So they cause extensive damage to the human cells. So apart from those general behavior of these radiation, now we can consider the effects of radiation on human beings into three categories. One is the short-term or recoverable effect, the long-term irrecoverable effect, and finally the genetic effects, which are in long-term in nature. So first is short-term recoverable effects, are those happen to those individuals who receive radiation directly. For example, when somebody goes for a radiotherapy, they are given doses of radiation. So these are the short-term recoverable effects. First is there is a reduction in what is known as white blood cell count. As we all know, blood consists of two types of cells, the red blood cells and the white blood cells. So white blood cell count. So when the radiation is increased, or when we receive radiation, there is a noticeable reduction in white blood cell counts. So white blood cells are the ones that attack external viruses, and they give the defense to the body. So those blood cell counts get decreased if one is exposed to radiation. These are recoverable effects, in the sense these are limited to a short duration of time, and then they get recovered over a period of time. Next among the short-term recoverable effects is hair loss and skin disorders. And third, we have diarrhea, vomiting and fever, which is also called as radiation sickness. So radiation sickness is a typical effect of short-term recoverable effect when one is exposed to radiation. And long-term irrecoverable effects include damage to bone marrow. If one is exposed continuously to radiation for a longer duration of time, then it is likely that the bone marrows get affected, they get damaged, and they can't heal basically. And that's one of the problems we have. So this damage to bone marrow, and it's likely that one gets blood cancer or leukemia, as it is called, when one is exposed to radiation for a longer durations of time. And it's also known that one can contract cataract of the eye when one is exposed to radiation for a longer duration of time. So these are a couple of examples for long-term irrecoverable effects. When I say irrecoverable, that means these are permanent in nature. You can't recover from this. So these short-term, long-term, and finally we look at genetic effects. These are effects that happen over generations of time, or generations of human beings. So when somebody is exposed to radiation and their offsprings get affected because of the genetic effect, because of what is known as the genes in the human body or the genes in the animal get affected because of radiation, and therefore this effect is carried over to the newer generation of the species. So genetic effects, some of them are mental deficiencies, or giant or monsters getting born, or general deterioration in quality and population number. The number of people who get born, or the number of species that can get produced get reduced, because of the genetic effects of radiation. So these are basically some of the effects of biological effects of radiation. So to recapitulate, short-term, long-term and genetic effects are broadly the effects that or the ones that broadly are felt. So short-term or recoverable effects, long-term irrecoverable effects and genetic effects that carry over from generation to generation. And also incidentally note that depending on the type of radiation, the damage is either less or extensive. So alpha particles have less penetrating power because of the size of the nucleus or the size of the particle. And neutrons, because they are electrically neutral, can penetrate to a larger extent. And then beta particles, since they are negatively charged and they are smaller in size, they have greater penetrating power compared to alpha particles. So these are some of the known effects of radiation. Now, after having looked at the biological effects of radiation, let us look at the last topic, that is some of the safety precautions. So these are some of the safety precautions that are being taken now to avoid receiving radiation. There are a couple of things we need to be aware of at this time. One is there are something known as background radiation that we are all receiving at all instances of time. For example, radiation is coming into Earth from different sources from outside of this Earth through the Earth's atmosphere. So we don't have any control over the radiation that is coming into us from outside of the Earth's atmosphere. So that is something we cannot even prevent. So this is known as background radiation, which we are all receiving. Likewise, from the Earth's crust, there could be some radioactive materials which are emitting radiation. So there is no way we can prevent that radiation from affecting us. So these are known background radiations that we are all receiving. However, to the extent possible, we need to prevent radiation from being from us getting the radiation from known sources. It is to be noted that both Marie Curie, who was involved quite extensively in working on radioactivity, as well as Enrico Fermi, another scientist, were exposed to large amounts of radiation while they were conducting experiments in the laboratories, and because of those large dosage of radiation that they received, both of them died with due to the effects of the long-term exposure to radiation. So it's a known thing that radiation does cause lethal effects on human beings. So these are some of the safety precautions that one can take while dealing with radioactive material. So the first thing is radioisotopes are handled by mechanical tongs and operated remotely from behind thick walls of lead or concrete. As we mentioned, the radioactive the emission from the radioactive material can be stopped if we have thick walls of lead or concrete, because this radiation have some kind of penetrating power. So depending on the penetrating power, if we have thick walls of lead or concrete, we can almost be sure that almost all the radiation are stopped before they reach us. And therefore radioisotopes are always handled by mechanical tongs operated remotely from outside of thick walls of lead or concrete. This is one of the ways we can prevent radiation from hitting us. The next one is thick-walled lead containers. When we transport radioactive material from one location to another location, we use thick-walled lead containers to transport radioactive material. They are thick-walled because of the thick wall here, the containers are going to prevent radiation from going outside of the box. Now the third aspect here is, in laboratories, radioactive materials are always stored in suitable lead boxes to prevent radiation from affecting individuals surrounding the material. So these are some of the precautionary measures that one can take, or one is taking at this time, to prevent radiation from affecting us. So with this discussion on safety precaution, a brief discussion, we come to a conclusion on the topic of radioactivity. So in this session on radioactivity, we looked at, just to recapitulate, we had a brief introduction to the topic. Then we looked at Soddy's group displacement laws, where we talked about the element giving out radiation and then getting displaced two columns to the left in the periodic table or one column to the right, depending on what type of radiation is given out. Then we talked about radioactive decay. We derived an expression for radioactive decay. Then we looked at decay constant, half-life, and then mean life. And then we looked at the units of radioactivity, which is basically becquerel, is BQ, abbreviated BQ. Then we looked at artificial transmutation, and then artificial and induced radioactivity, wherein we said for all the elements we can induce artificial radioactivity. And then we looked at radioisotopes and then their applications, biological effects of radiation, and finally we discussed about some of the safety precautions that are being taken to prevent radiation from affecting the species. I hope you have understood this topic pretty well. Thank you very much.